In lesson 8.4, we're going to learn how to work with something called the standard normal distribution. When the distribution of an athlete's performances are roughly symmetric and bell-shaped, we can often use a normal distribution to model and make predictions about their performances. The histogram that's shown in your notes shows Peyton Manning's distribution of passing yards from 1998 to 2008. And during that 10-year period, his performances took this normal bell-shaped curve with a mean of 259 yards and a standard deviation of 74 yards. And so, even though the histogram itself of performances isn't a perfectly normal curve, we can draw a normal curve on top of the histogram. And even though it doesn't fit perfectly, it's good enough. We will never have any situation where we have real data that we've collected from an athlete or a team that will be exactly normal. So, we are going to use the normal distribution to approximate that. Now, the problem is that there are an infinite number of normal distributions because for every football player that we looked at, or every baseball player, we took their batting averages, basketball player with the number of points they scored, each one would have their own normal distribution with their own mean and their own standard deviation. So, to make things simpler, instead of having to draw an infinite number of curves, we're going to convert all of these distributions to standard normal distributions, which would therefore be a distribution of z-scores. So in the curve on the left, you can see the curve labeled with Peyton Manning's mean and standard deviation. However, if we turn those all into z-scores, we would get what's called the standard normal distribution. Now, remember, for the z-score calculation, we take a performance. For example, if we take this performance right here, which is at the center, so his performance there is 259 yards, and we subtract the mean from it, which in this case is 259 yards. We divide it by the standard deviation, right, which is 74. That gives us a z-score of 0. Now, if we repeat that calculation, but instead of using 259, let's say we do it for 333. So 333 minus the mean of 259 divided by the standard deviation of 74. Well, that's 74 over 74, which is 1. That gives us a z-score of 1. So I think you can see pretty clearly here what's going to happen. We have positive z-scores on the right, negative z-scores on the left, and this is what we refer to as our standard normal distribution. Now, some properties of the standard normal distribution. The curve is symmetric and it's centered at the mean. The curve approaches the x-axis but never reaches it. The total area under the curve is 1 or 100%, which will be important as we do some calculations. And the standard normal distribution will always have a mean of 0 and a standard deviation of 1. So regardless if we're talking about passing yards, points scored, batting averages, we're going to standardize everything. So the center will always be at 0 and the standard deviation will always be at 1. Now, in your packet, you have a copy of Table A. And Table A looks like this. It's labeled AP Statistics Free Response Questions at the top, because we use this in AP Statistics quite a bit, but I've provided you with a copy of this table as well. And notice that the table has two sides. So the top, it has a picture of a standard normal curve. And notice that here we have the portion that's shaded in, and it's shaded into the left of that line that's labeled with a Z. And then we have some numbers in the margin of the table. Notice that we have a Z here in this corner. And then on the other side of the table, we have something that looks similar, but now notice that Z is to the left of the center of that curve. And on this side, Z is to the right of the center. The other thing that you might notice is different is that when you look in the margins of the table here, we have positive numbers. And on the other side of the table, we have negative numbers in this margin. So that's going to be important. Now, standardizing the normal distribution allows us to find the area under any part of the curve using the standard normal table, which shows the area under the curve to the left of any z-score. And that's why in Table A, the picture at the top shows the shading to the left of that vertical line. So in your notes, it kind of gives you an example. So we have a picture of the standard normal curve. Notice down at the bottom, we have a vertical line that's drawn in here separating the curve into two regions. And underneath here, this is labeled Z equals 0.81. Notice it's just shy of positive 1, which is about where 0.81 would be. Now, the area to the left of that, if we want to find the area to the left of that, we use table A. And because our z-score is 0.81, we separate that into the tenths place, which we look for in the left-hand margin of the table. And then the hundredths digit, the point or the 0.01 there, is where we look in the top margin of the table. And where that row and column intersect, we have a decimal that goes out to 4 places. And that tells us that the area of this shaded region is 0.7910. Now, the nice thing about this table is, first of all, it allows us to be a lot more precise than we were in the last section when we were just sort of estimating 34%, 16%, and so on. Here we can go out to 4 places so we can be more precise. The other thing that's nice about this is that we don't have to just look for areas to the left or to the right of 1 standard deviation or 2 or 3. We can go for any value in between. So in this case, we did 0.81 standard deviations, which we were not able to do in the last section. All right, so in these examples that are in your notes, what the directions say to do is to shade the area of interest under each curve and then find the area or proportion of the shaded region. Letter A says Z is less than 1.52. So the first thing we're going to do is we're going to try to estimate here where 1.52 is. It's going to be between 1 and 2. The inequality symbol in this problem says less than, and less than in this curve would be everything to the left of that line. So we'll shade in everything to the left. Now, to get that area, we're going to go to table A. And because we're dealing with a positive z-score, we want to be on the front side of the table where the z-scores are positive. The z-score we're looking at here is 1.52. So I'm going to look in the row that has 1.5 over in the left-hand margin. The second digit of my z-score is a 2, so we look in the column that says O2, and notice where that row and column intersect is at 0.9357. And so the answer to this question then is 0.9357. And it's always a good idea to kind of ask yourself if your answer makes sense. Does it look like 93% of that curve is shaded in? I would say it probably does. We have almost the entire thing shaded in there. Letter B, Z is greater than 0.6. 0.6 is, again, positive, and it's between 0 and 1. This time our inequality is greater than, so it's going to the right, and we want to shade into the right of that line. Now we go to table A. Our z-score is 0.6. So we look in this row right here where we have z is 0.6. There is no second digit or no digit in the hundredths place, so that means we use the 0.00 column, and where those intersect is 0.7257. Now, notice when we look at our picture that we clearly have less than half of that curve shaded in, but the number we got from table A was more than 50%. Why did that happen? Well, that 0.7257, remember, is the area to the left of that z-score. That's the unshaded region. So to get the area to the right, remember that the total area is 1, or 100%. We would do 1 minus the area to the left, and that would tell us the area on the right, which is 0.2743. Let's look at letter C. In letter C, we're looking for the area between two z-scores. So here we're going to have to use our table twice. First, let's mark off our region. Negative 1.04 would be right about there. And positive 2.31 would be way over on that side. And we're looking for all the area in between those two regions. Now, what we're going to do with table A in this case is we're going to look up the this z-score first. And if we look that up on table A, it's going to give us the area of everything to the left of that. All right. Well, we don't want everything to the left of that. We want everything except this. So if we then look up this z-score on table A and we subtract those two areas, it's going to take this whole area and it's going to subtract off this part that I don't want. So that's the approach that I'm going to take. So first I'll look up the 2.31, and I would look in the 2.3 row, the 0.01 column. That gives me 0.9896. That's everything to the left of the positive z-score. Now I'm going to flip my table over, and my negative z-score was negative 1.04. So I'm going to use the negative 1.0 row and the 0.04 column, and that gives me 0.1492. Now, the area in between would be the difference of those decimals. And because we're finding an area, remember that your answer always has to be positive. So if you subtract those in the wrong order, you'll get the right number with the wrong sign. So just try to remember that we're looking for an area, and areas always have to be positive. Now let's do letter D. D is looking for the area between -1 and +1. So we'll draw our lines in there and we'll shade in that in between region. Now we learned yesterday that that area within one standard deviation of the mean should be about 68% of our data. That's what the empirical rule told us. We're going to calculate that now with table A and see how close that approximation is. So just like we did on part C, I'm going to look up the two z-scores and then subtract. So if I look up a z-score of +1, I get 0.8413. If I look up a z-score of -1 on table A, I get 0.1587. And the difference there is 0.6826. So pretty close to what we were estimating with the empirical rule. But here we're able to be more precise because we're going out to 4 places instead of just 2. All right, there are 2 more examples for you to try in your notes. I would suggest that you pause the video, try them on your own, and then restart it to check your answers. All right, for part A, we're looking for the area where z is greater than -2. So I mark off a vertical line at -2. I want to shade the area to the right. Now, when I look up a z-score of -2 on my table, I am given a very small area, this 0.0228, which is the area to the left. That's the unshaded region. So I want to subtract that from 1. That gives me a final answer of 0.9772. Last but not least, we're looking for the area between -1.78 and -0.05. Notice that those are both negative. I'm going to look up the -0.05 first because that one is bigger, and then subtract the area to the left of -1.78 from that. When I did that, I got 0.4801 minus 0.0375 for a total area of 0.4426. Please do homework 8.4 in your assignment packet.